Hello, welcome to my talk on derivations of Bernoulli's equation. This is the third part of the talk on this topic. This is on the derivation of Bernoulli's equation for incompressible potential flows. In this talk, I will first introduce the Euler equation in a vector form, and then I will introduce why we need to derive the Bernoulli's equation for potential flows, and we will discuss the assumptions of potential flows, then the derivation of the unsteady Bernoulli's equation for potential flows step by step, and last, a simple application of the unsteady Bernoulli's equation for the free surface boundary condition in the ocean wave. In this slide, I would like to introduce the fluid dynamic equation, the Navier-Stokes equation. We have three momentum equations. The first one is along x-axis, and second equation is along y-axis, and the third along z-axis. If we write this Navier-Stokes equation into a vector form, it would be given as this. And we can see this part is corresponding to the partial differentiation of the velocity vector with regard to t. And u, v, and w are the velocity component along x-axis, y-axis, and z-axis. And this is the fluid gravitational force per unit mass. Here, vector k is the unit vector along z-axis. So we see there's no component of the gravitational force along x-axis and y-axis. And this is the force due to the pressure, and these are the diffusion term for the Navier-Stokes equation. And the most complicated term are this so-called convective acceleration. So this can be written in a very simple expression as this. Now we have looked at how these terms can be written as this. We see this vector v dot timing the Laplace. Both vector v and Laplace are vectors. V, we write this into three components, and the Laplace is expressed as this. And the dot timing them together, we have the expression as this. And we can see the result of the dot timing of two vectors, vector v and the Laplace. It would be a scalar given as this. And if we time the component u, v, w to this expression, so we have the expression here. And this three components along x-axis, y-axis, and z-axis are exactly the same as this. And put all this together, we have the expression in a vector form as this. And the Laplace expression is the Laplace squared equaling to Laplace dot timing Laplace. And we have this expression dot timing this expression. And we have the expression as this. These are the Laplace operator. So if we apply this velocity component u, v, w, and put all this together, it would be a Laplace operator of the velocity vector. Now in this slide, we will see the comparison of the general Bernoulli's equation. As we have known before, the general Bernoulli's equation is derived from the Euler equation for inviscid flow, and it is only for a steady flow. It is valid for incompressible flow. and the general Bernoulli's equation is only valid along the fluid stream lines. For potential flows, it is the same. Both are from the Euler equation for inviscid flow, since potential flows is essentially an inviscid flow. But here we don't need to assume the flow is steady. For potential flows, Bernoulli's equation can be unsteady. We will see an example in this talk later on. And here we consider the incompressible potential flows. And for potential flows, the Bernoulli's equation is valid for the entire flow field, not necessarily valid only on the fluid streamlines. This could simplify the problem very much. When we apply the Bernoulli's equation for inviscid flow, one question would be how we can obtain the streamline for the Bernoulli's equation. For instance, for the pipe flows, we see all these streamlines. But even for this simple problem, it's very difficult to obtain the streamlines exactly. So when we use the Bernoulli's equation, in fact, we don't actually use the Bernoulli's equation on the streamlines. Instead, we apply the Bernoulli's equation for the potential flow in the pipe, since when the Reynolds number is large for the flow in the pipe, the most of the flow can be regarded as the potential flow. Only the small part near the pipe wall is rotational flow. And in that case, we can apply the modification method for modifying the flow, so we can still get the correct answer by using the Bernoulli's equation with the modifications. And for a more complicated flow, the flow past an airfoil, the question is how we can get the streamline for the flow. Like this. In here, the fluid path line and the streamlines are same, but this is only possible when we solve the problem of the flow dynamics. And in that case, the Bernoulli's equation would not be that important, since we already obtained the parameters in the fluid. So the question again, whether we need the application of the Bernoulli's equation along the streamlines. In such a problem, we normally assume the flow along past the airfoil is the potential flow, so the Bernoulli's equation can be correct in the entire flow domain. This would much simplify the problem. The another problem is the flow of the water wave. So the streamlines we can see here are unsteady flows, and the streamlines would be time dependent. It's changing with the time. And the question is how we can get these streamlines and how we can apply the Bernoulli's equation for such a flow. In fact, we don't actually apply the Bernoulli's equation along the streamlines. Instead, we assume the flow for the water wave is potential flow, so the Bernoulli's equation is valid in the entire flow domain. This is why the Bernoulli's equation for potential flow is more important and more applicable than the conventional Bernoulli's equation, since the application of Bernoulli's equation for the potential flows, we don't need to find out where is the flow streamline. We can apply the Bernoulli's equation for the entire flow domain. Now in here, we look at the assumptions for the incompressible potential flow. For potential flows, the core of the velocity vector is 0. The mathematical expression is given as the Laplace cross-terming the velocity vector is 0. This is the expression, which means the three velocity components are not independent anymore for the potential flow. For such a potential flow, we can use the scalar function, the velocity potential function phi, and from the potential function we can define the velocity vector v as this. It is the gradient of the velocity potential function. If we define this, and we can see the core of the velocity vector, it's calculated this, and this is identically 0. This means the velocity potential function would guarantee the core of the velocity vector is 0. And the potential flows are inviscid flows. Thus, the viscous term in the Navier-Stokes equation would vanish. So the Navier-Stokes equation would become the Euler equation given as this. Now we are going to derive the Bernoulli's equation for the incompressible potential flow. Based on the Euler equation, the vector form, here we have 4 terms. We term these terms 1, 2, 3, and 4. So for the local acceleration term, the first term, the partial differentiation of velocity vector with regard to t. And if we apply the velocity vector using the velocity potential function, then we have the expression as this. And we can change the order of the operation, nabla and the partial differentiation. We have the expression as this. This is the conservative term because we have the nabla outside of this expression. And in deriving the Bernoulli's equation for incompressible potential flow, we need to get all these terms to be expressed as the conservative term. The second term is the convective acceleration. Here, if we use the calculus identity expressed as this, if we let vector A and B are both vector v, so this would become this. So we have the expression as this. And consider the potential flow, the core of the velocity vector is 0. So this term would vanish. Thus, the convective acceleration can be expressed as the conservative form as this if the flow is assumed as the potential flow. And we have a look at the third term for the body force of the fluid. This expression can be expressed as this, the conservative of the expression Gz. This actually equaling to the expression, the gradient along x-axis, the gradient along the y-axis, and the gradient along z-axis. Consider the function Gz is independent of x and y, so these two terms would vanish. Thus, we have the expression as this, so this can be expressed as this. And for the pressure term, since we consider the incompressible flow, so the density of the flow is constant. Thus, we can easily write this expression into a conservative form as this. Therefore, the Euler equation can be written as this. So all these 4 terms can be expressed as the conservative form as this. And we can write this equation into a form of this. This is the Euler equation for incompressible flow, and it is in an integrable form. So for this conservative form of the Euler equation, we can simply integrate the equation. So we have the expression as this. This is the unsteady Bernoulli's equation for potential flow. And here C0t is the integral constant. It is a time-dependent constant because the integral from this into this is on the spatial component, not on t. If we take the gradient of the Bernoulli's equation, it would be given as this. This is exactly the same as this. So now we can see the Bernoulli's equation for the potential flows. It is an integral form of the Euler equation because this is the integral of this integrable Euler equation for potential flow. And the Bernoulli's equation is applicable for unsteady potential flows. And this Bernoulli's equation is valid for the whole fluid domain. This is very different from the general Bernoulli's equation, where the Bernoulli's equation is only valid on the streamline. Therefore, the Bernoulli's equation for potential flow is more useful, since we can find out the velocity distribution in potential flows by solving the potential function, other than to find the flow streamlines. It is difficult to do that. For instance, the flow field in the water wave or the flow past the airfoil. The streamline is very difficult to find, while the velocity field can be solved from the Laplace equation. We will see in the future in my talk. Next, we would have a look how the unsteady Bernoulli's equation used for the water waves. See here the plot for the water wave. We have free surface here, and on the free surface, the atmospheric pressure is P0, and the water depth is H. See this? We assume the water is the potential flow, so we can use the velocity potential function to express the velocity vector v. For the unsteady Bernoulli's equation, it is given as this. Here C0t is the time-dependent integral constant. However, for the water waves, we can choose C0 equaling to P0. So the unsteady Bernoulli's equation is given as this. Here we can see if we reduce the wave amplitude to 0, that is the calm water, so the corresponding velocity potential function phi would be 0 or a constant. And at z equaling to 0 on the calm water free surface, the pressure is the atmospheric pressure P0. Thus, we can see C0 chosen as P0 is correct for this application. Then we write the Bernoulli's equation in a form as this by moving the pressure into one side and the left terms on the other side. Here, we are not using the velocity vector, but the gradient of the velocity potential function. And we will see later this is necessary. So on the free surface, see here, z would equaling to eta 0. This is the free surface expression at the water surface. And on the free surface, the pressure would be the atmospheric pressure P0. Thus, P minus P0 is 0. Then we can calculate the free surface elevation eta 0 given as this expression. So this is the full dynamic boundary condition for free surface. However, in the application of the wave, this term would be the second odd term compared to this partial differentiation term. It would be smaller than this term, thus this can be dropped. Then the wave elevation eta zero can be expressed as this expression. This is a linearized dynamic boundary condition for 3 surfaces at z equaling to 0. Next, we would like to have a look at the kinematic boundary condition for the water wave. As we have shown, on the free surface, we take z minus eta 0, so it is 0 on the free surface. We take the substantial derivative of the parameter z minus eta 0, given by this, so it is 0. And we have the expression as this. This expression actually means we have 2 different ways to calculate the fluid particle velocity along z direction. This and this are same but use a different form. So the first term would be the velocity component along z direction. But this term would be different because eta 0 is a function of x, z, and t. So the calculation of the substantial derivative of eta 0 with regard to t is given by the partial differentiation of eta 0 with regard to t plus this and this. And we can write this term using the velocity potential function. W is the differentiation of phi with regard to z. U is the partial differentiation of phi with regard to x. So these are the exact kinematic boundary condition for the free surface. However, if we look at the expression, this term and this term are the second order term compared to the first 2 terms. So these 2 terms can be dropped, and the kinematic boundary condition can be linearized as this. So this is given at z equaling to 0. Now put the kinematic boundary condition and the dynamic boundary condition together. We can obtain an equation for the free surface given by this. This is a typical wave equation. That means the surface is a form of a wave. Also, the velocity potential function phi would satisfy the Laplace equation given as this in 2 dimensions. If we include the boundary condition at the seabed given as this, the velocity at the seabed on z direction is 0. This is a no penetration condition, means there is no flow through the seabed. If we solve the equations 1, 2, 3 together, we should have the potential function for the linear wave given by phi as this. Here A is the wave amplitude, omega is the wave frequency, and K is the wave number. I will make a talk on this in the future. So here, just to give you an idea how we can use the Bernoulli's equation for the water wave.